Hello, in the final video of the series on Taylor series, we're going to have a look at interpolation. First of all, how to do interpolation intuitively, and next how to use Taylor series to find interpolation formulae. We assume that we're going to have a function f, which is known. We have known values at positions x1 and x2, so it's known to be f1 at x1 and f2 at x2. We want to estimate a value in between. At position xi, we want an estimate value fi. So as an exercise, I'd like you to think about how to use linear interpolation. So i.e. assume that fi lies on a straight line in between x1 and x2, and find a formula for fi in terms of the known values. So you can use f1, f2, these positions, x1, xi and x2. And as a hint, first of all write down equations for delta x as the difference between x2 and x1, for beta, which is the fraction of this length, fraction of the length from x1 to xi is as a fraction of x1 to x2, and the gradient of this line, and then find an expression for f at xi. So you should pause the video and have a go with that before I move on. Moving on now. So delta x is x2 minus x1. Beta is this distance divided by that distance. And then the gradient is the difference between those divided by the difference in those. Now we can find an equation for fi. So it's going to be f1 plus the gradient times that distance. And that can be rewritten in terms of beta. So it's a blend between f1 and f2 depending on how far along it is along this line. So in this situation we know 2 points and we can find a linear polynomial to estimate f. If f is known at n points, then we can find a polynomial of degree n minus 1 in order to find f. And in particular, an example that's already worked out, cubic-Lagrange interpolation, if we know 4 values of f, so we know f at k minus 1, k plus 2 and k plus 1, this cubic-Lagrange interpolation formula gives you a function for f at any point based on those, using this value beta. So these interpolation formula can be found using Taylor series, and I'm going to go through an example. So I'm going to assume that we know fj at position xj, fj plus 1 at position xj plus 1, and we want to find the interpolated value f of j plus a half, midway between xj and xj plus 1. So we'll start by writing Taylor series for fj and fj plus 1 centered around position j plus a half. Here are those Taylor series. I've included quite a lot of terms. So they're all in terms of j plus a half. We probably won't need this many terms, but I'm including more just in case. So we want to eliminate the largest unknown. The largest unknown is f dashed of j plus a half. These are the knowns. This is what we want to find out, so we eliminate this by adding the two equations together to get this formula. We want to find this, so we need to rearrange and then express the error based on the largest unknown. So this turns out to be the largest unknown, so the error is proportional to delta x squared. We rearrange to find fj plus a half. As you can imagine, given if fj plus a half is midway, it's just the average of the two. But what we know from this, having used the Taylor series, is that this is a second order accurate approximation. So as delta x gets smaller, the error will get smaller proportional to delta x squared. So here's some more exercises using Taylor series with the answers at the end, and so the rest of this document is the solutions for the exercises. So that concludes this series of videos and these notes about Taylor series and their uses, some of their uses in numerical analysis. Thank you.